Okay, so the recording has officially started. Now I want to show you, before we talk about some material from chapter 1, I made a couple of changes to the calendar. There's some things that weren't quite syncing up. So what I did was moved a few things around. Nothing is due any earlier than it was before. So if you started working on things, you can continue to work on things. So I want to kind of, as I said, sync some more assignments up. So the only thing I have to do at the end of today is the introduction to the MyOpenMath system. So if you already completed that, you're done. Assignments for the week, perfectly fine. The way it's going to be set up is you're going to do the online homework before you turn in the weekly homework for particular sections. So the first online homework is due Monday. And it's going to be sections 1.1 through 1.4. And then the weekly homework, which is usually going to be a day or 2 days afterwards, depending on when the online homework is due, will be over the same sections. So this is the homework you want to do first. It's there for practice. As I showed you in class, you're working on it until you essentially get tired of it, until you get it right. And then you'll do the weekly homework. That's what you turn in either in class or you can upload it to MyOpenMath. Now, a couple of these assignments are going to be a little cramped because of our first week of class here, but I'm going to try to keep a schedule with online homeworks mostly due Tuesdays and weekly homeworks due Wednesdays. I've put aside Fridays for quizzes and exams. And you'll notice I've also scheduled the Precalculus technology project due dates. So those are going to be on Mondays. That gives us a chance to talk about the previous Friday. And then you can turn those in at the end of the day through MyOpenMath. So you have a couple of times during class you can ask about those. But I got pretty much everything worked out until right about here, up to about quiz number 2 for now. So online homework done first, weekly homework done next, and they're pretty much over the same sections. So as you're working on this, you can help yourself with the problems that you see here. Quiz number 1, if you click on quiz number 1, is going to be over the first 2 chapters, chapters 1 and 2. So we're going to be finishing up today and then everything in chapter 2. And then quiz number 2 is going to be over chapter 3. And then, as I said, our first midterm is going to be on algebra, and that's going to be right before spring break. So quiz number 3, I think, is over chapter 4. I have that written out right here too. So this gives you a chance to kind of look ahead if you want to work ahead a little bit. Pretty much all of the assignments you see in a given week are for material that was done in the previous week. So if that's something you have to do in class one day and then work on an assignment that's due the next day, it gives you a little bit more time to learn the material and practice with the online homework, and then before you turn in your weekly homework. And then everything you see here up through weekly homework number 2 is going to be part of that first quiz. So we're going to be done with chapter 2 by the end of the second week. That's all going to be on that quiz. We'll be done with chapter 3 by the end of this day right here, the 11th. That's all going to be on quiz number 2. That gives you a chance to review, learn, relearn things, not just, here's what we did today. Hey, let's take a quiz over the next time. That's not the way it's going to work. So I wanted to let you know about the changes in the calendar before we got going here. So any questions about the calendar? You'll notice the color coding here. Red is urgent. That means, it's essentially due today, and it's due today at 11 o'clock. Orange means it's coming up a little faster than the yellows, and then the greens, you got a little bit of time to work on those. Those are a couple weeks off, as you can see. So any other questions about the calendar? Great. So what I thought we could do is just kind of go over, we might repeat a few things that we did on Wednesday in chapter 1. But as I said, chapter 1 is a very important chapter. It's the definition of a function. You do functions all over in calculus. You analyze functions, talk about rates of change, talk about areas under graphs, things like that. So the notation is important, vocabulary is important, definition is very important. So we're going to go over the items in chapter 1, which talk about the different vocabularies, notations for functions. And then for chapters 2 and 3 and 4, we're going to analyze particular types of functions. So linear functions, quadratic functions, polynomial functions, rational functions, absolute value, I say rational functions. And then the last two are the exponential and logarithm functions in the algebra section. And then when we start trigonometry, you'll of course have the trigonometric functions. So a solid understanding of chapter 1 is going to be very important to have success in later chapters. So where does it all start? It all starts in section 1.1, the definition of function. So we kind of looked at this definition on Wednesday. We had a shorthand version of the definition, but if you were to draw a picture, and I say this set identifies the first set of items. So they could be numbers, they could be objects, they could be anything. We're really talking abstract here. And this is your second set. There's going to be a relationship between the items in the first set and the second set. So if I identify some of the items in the first set, identify some items in the second set, just throwing some letters out there. You're going to then define a relationship between these two sets. So to A, I'm going to relate X from the second set. B, I will relate Y from the second set. And C will be related to Z in the second set. So this is one way to show a relation between two sets. Sorry, I'm going to work on my pen here. There we go. So this is an example of a relation between the two sets. But as you probably know, the definition of a function is actually a subset of the definition of a relation. So if we just have a relationship between two sets, when is it going to be a functional relationship? And that's where we talk about the restrictions. So if each element of the first set, which is right here, is related to only one element in the second set. So as I said, this is a more abstract definition. You're talking about objects. You know, a lot of times in math, we talk about numbers, but in general, these are just objects. So A is related to X, B is related to Y, C is related to Z. And this is the key to the definition. If each element here is related to only one element here, then you have what's called a function. So if you set up another relation, say A is related to X, B is related to Y, but B is also related to Z. So using the red arrows, that's still going to be a relation between the two sets, but is it going to be a function? What happens to element A from the first set? It is related to only one element. But what is related to element B from the first set? Some people would say it's related to Y. Some people would say it's related to Z. And you're both correct because that's what the arrows are telling us. So using the red arrows, this is not going to be a function. So that's the key to the definition. Each element from the first set, order doesn't matter here, is related to only one element from that second set. The other thing to make sure you understand here is function representations. You can work with describing functions using words. You can draw a picture. You can have a table of values or ordered pairs if you want to put them that way. Or you could be looking at an equation. And one thing our book does a very good job of is it gives you examples from each of these types. There are some numerical problems. There are some functions that are described in words. There are some functions where you're looking at a picture. This is an example of a picture here. Or equations. We want to make sure the notation is consistent. We talked about the first set and the second set. So here are some functions in each of the different representations. So here's a table. I give you the first set, usually call it X, second set, call it Y. If I identify the elements in the first set, and here are the elements in the second set. And I would ask you if this was a function or not. You would hopefully say yes. Because if I say what item is related to X equals 0, according to the table, it should be Y equals 5. If X is 3, then Y is -1. When X is 2, Y is 10. Each time that X value is related to only one Y value. Now, does there need to be a formula here? No. As long as you have a table of values that says what happens to 4, what happens to 3, what happens to 0. If you have the second row here identifying what happens to your inputs, that's all you need. The equation, a lot of students are thinking it's got to be an equation here. Why don't we see a formula that works? It still satisfies the definition. So if you want a formula that works, here's a formula that works. If I give you X, you multiply that input by 3, and then you add 4, you get a corresponding Y value. The question is the Y value unique? So we do 3 times 2 plus 4. We do 3 times -1 plus 4. We do 3 times 1/2 plus 4. In each of those cases, will you get a unique Y value? And the answer is yes. But once again, order does make a difference here. We usually call the first set the values for X. The second set, we usually use Y. We sometimes use the term inputs and outputs for this right here. So if these are the inputs and these are the outputs, we're looking at functional relationships here. And that's also important when you're graphing, because when we graph things, X is always going to be our horizontal axis, and Y is always going to be the vertical axis. So when I draw a picture, I say, is this picture representing a function? When we say function, is Y a function of X? So here's a picture. I'll draw a couple for you here. Here's another picture. And here's another one. Of those 3 graphs, you'd say which ones are functions. And when you say function, you don't always have to say Y being a function of X. That's our usual way of representing things. So given X, can you calculate Y, first of all? And when you calculate Y, is it unique? For the dark green graph, yes. I pick an X value. I go up to the graph and say, it looks like there's only one Y value for that one. Do that for the red graph. Pick an X value. Here's my corresponding Y value. But if you take a look at the sort of lightish green graph here, I try to do that same thing. I pick an X value. It looks like I have 2 different outputs. So a lot of you are thinking vertical line test here. That's exactly what you do when you are looking at a picture. So if you draw a vertical line, which represents an input, if that vertical line intersects the graph more than once, the definition is not satisfied. So the light green graph is not going to be a function. And that's the only one. So once again, order makes a difference. If I draw a horizontal line here, it will intersect the graph twice. But a horizontal line represents outputs, not inputs. So a vertical line test for functions. When we talk about one-to-one functions, we're also going to consider what's called the horizontal line test. Okay, and then in words, you can just describe the first set, describe the second set. So let's say the first set is everybody in class. And then the second set is going to be your ID number. So I would ask you, would that be a functional relationship between those two sets? And all you have to do to answer that is, you are the student. If I were to ask you what your ID number is, you don't have to give it to me because I can look it up. But when I look it up, how many ID numbers are there for each person? One. That's why I call it an ID number. It tells us, or tells me, who you are as a student. So that's an example of a function as well. Now, is there a formula that calculates your ID number? No, you don't need a formula. You just need to know, does each element from the first set relate to only one element in the second set? If that is true, we have a functional relationship. I mean, isn't that what ID numbers are supposed to be for identification purposes? So if you have more than one ID number, you're not going to be identified properly. So think about ID numbers, credit card numbers, things like that. So these are the four representations. We mostly do, I'm just going to say mostly, but we do all the other versions as well. We mostly do equations and pictures, graphs of equations. Sometimes we can do all four. Sometimes we can do pictures and equations. You can turn it into a table if you want to. One of the things we're going to be doing a lot this term is taking something that is maybe a picture or maybe a table of values and turning it into an equation. With the equation, we know how to draw a picture from the equation in a lot of cases and trying to identify what kind of function we have. So once you know you have a function, you can then replace the outputs with our specific notation that relates it to a particular input. So this is our function notation. This is read y is a function of x. So this is not supposed to be read as times. It's more of a notation saying x is going to be our input. So if I give you the input, you use the definition of the function, whether it's in words, picture, table, equations, to calculate the corresponding output. So it gives us a way to actually specify what does the output look like for a given input. So if you're looking at a formula for this one, so I'll just write down a formula. There are a couple different things you can do with the formula. You can give me an input, as long as it's in the domain of the function. What does this mean right here? F of x is equal to x squared minus 3x. If x is replaced by 1, the formula should be the same. X should be replaced by 1. Can we simplify and get a corresponding output? Yes. Is it unique? Yes. You're not going to use this notation if you do not have a function. So this is going to be -2. So in the end, we would say f of 1 is equal to -2. So that direct relationship between inputs and outputs. Input is 1, output is -2. Now, if you understand how the function notation works, you could also do something like this. What would f of h be equal to? A natural question here is, what's h? Well, h is a variable, just like x is a variable. Some books describe it as like a placeholder, something, if you didn't even have a letter there, you can kind of write your function like this. I'm not a fan of this notation, but this is how some books describe it. Think of it as a placeholder. Whatever I put here goes in these two slots when you're evaluating the function. So it doesn't matter whether you have a number, a variable. I guess you put a shape in there if you want to, but it's not going to be very helpful. Whatever goes in here, x is replaced by that expression, number, whatever you put in there. And then you do what you can in terms of simplifying. Here, we could write this as -2 because we started with x equal 1. Here, if x is equal to h, that's the best we can do. I suppose if you want to factor it, you could do that, but you can't combine these. These are not like terms. And that's it. That's all you have to write down. You can even do things like f of 1 plus h. And now we have a two-term expression replacing x, and then your simplifying gets a little bit more interesting. I've already run out of room here, sorry. Because then you have to square a two-term expression. You know how to do that. And then distribute the -3 here. So you can put whatever you want in here. It could be essentially another function, could be a variable, could be a number. So the terminology we use for functions, your first set are known as the inputs, your second set known as the outputs. The more technical terms that we're going to call the first set and second set in section 1.2 are domain and range. Not sure why this is in a separate section, but I think they want to make sure you understand the vocabulary. So the domain is essentially the inputs, elements from the first set, x values. Those all really mean the same thing. The range, output, elements from the second set, or the y values. So all those are synonymous. So I like to remember it this way. Domain, first set, give me a number, give me an expression, tell me what to do with that expression. Then the corresponding output, which is in the range, comes from that second set. So these can be completely different sets. They could be numbers, they could be variables. Just important that when you define a function, you need to say what is the first set, what is the second set. All right, as you can see, I'm already out of room. So if you want to take a picture here, save the screen, go ahead and do that. I've got the start over here. And we talk about section 1.2. Any questions about anything so far?
I do have a quick one. So when you did f of 1 equals -2, is it right that that could also be written as an ordered pair, 1, -2?
Yes.
Okay, I just wanted to make sure that was okay.
I did not write that representation, but this is when you're trying to relate equations and pictures. If you wanted to graph this function, this would then be a point on the function. So these two are equivalent, yes. They'll just say the same. And ordered pairs, same way. First part of the ordered pair is x, second part is y. We always write our ordered pairs that way. So horizontal for x, vertical for y. It's easy to kind of get turned around there. So you're doing horizontal, vertical. So inputs, outputs. All right, one more chance to take a picture here, and I'm going to clear up the screen. And then take a look at what are called toolkit functions. Now, when you talk about the toolkit functions, these are the kind of building block functions that we use to talk about like a general linear function or a general quadratic function. You should be able to go from the equation to the graph, identify all these features of the graph without thinking too much. So here are some toolkit functions. I put these in the polynomial category. So x, x squared, and x cubed. I put these in the inverse category. We'll talk about inverses at the end of the chapter. And then other ones, absolute value of x, 1 over x, and 1 over x squared. So I just want to tell you, our book includes these as toolkit functions. To me, they're a little bit more advanced than just a regular toolkit function because of the fact that the domain for these functions is going to be restricted. So you can take a look at them. We're not going to be spending as much time on these toolkit functions as we are with the other ones. Not until we get to chapter 3, last part of chapter 3. So if I were to draw one of these toolkit functions, you should be able to identify the equation. So here are a couple of the toolkit functions. And these are, no scales, just kind of a general idea. What does it look like? They got all of them there. 1, 2, 3, 4, 5, 6, 8. Okay. Oh, that was a bad picture. Sorry. And then, okay. Right, so you should be able to go from the equations to the pictures and vice versa. So do a little mix and match here. X is what we call the identity function. Here's your graph. This is the graph of the square root function. Here's the graph of the cubic function. Here's the graph of absolute value. Here's the graph of the parabola, x squared. And that leaves us with the cube root of x, which is right here. And then the two reciprocal functions, 1 over x and 1 over x squared. So there's a nice neat picture for you there. If you're trying to practice things on your graphing calculator, make sure it's working all right, and type in these relatively basic equations and see if you come up with the graphs that you see here. So notice that the ones that have restricted domains, square root of x, and also these two functions right here. This one's called the reciprocal function, and this one's called the reciprocal squared function. And if you look at the graphs, I know there's a restricted domain here, but all these graphs to me look very similar. These are the only two that look different than the other ones. And that's because of this problem in the denominator. You have x in the denominator. I try to use x equals 0 as an input. You can't find a corresponding output. So there's something going on here that you can see in the graph. That's not going to be discussed, as I said, until the end of chapter 3. So you can call them toolkit functions. I will not be using those as much as these other ones. In the beginning, we're going to be doing polynomial functions first, absolute value functions. And then these are examples of inverse functions. So you want to make sure you identify the domain by either looking at the equation or looking at the graph of your function. When you're trying to identify the range, it's not as easy to identify the range just by looking at the equation, for example. So if I were to ask you, without looking at a picture, what's the range of the cubic function? You might think for a minute, is it possible to have all positive numbers in the range, for example? Is it possible to have negative numbers in the range? And is there going to be any restriction? Because as you can see, this picture right here, this picture right here, and this picture right here are going to have some restrictions in the range. But how do you tell just by looking at the equation? Not as easy to do. So a lot of the questions in section 1-2, when they talk about domain, will ask you to find the domain. They'll give you a function. They'll give you the equation. They'll give you a picture. You can just identify it from there. You won't be asked about the range unless you're looking at the picture. So this one has a restricted range. This graph has a restricted range. This graph has a restricted range. So with the toolkit functions, you want to be able to identify the equation, identify the graph, talk about things like domain and range. The other feature we're going to be emphasizing here is the idea of an intercept. There are two different types of intercepts. You could have x-intercepts and you can have y-intercepts. So the definition of an x-intercept is where does the graph intersect the x-axis. Definition of the y-intercept, same way except replace x with y. So if you look at these graphs right here, you can identify those points, and some of them are the same, where the graph intersects the x-axis or the y-axis. So the blue dots indicate intercepts. So 0, 0 is actually an intercept for all of these graphs that you see here. Once we start moving around, we'll change up where the intercepts are. But intercepts are points. And notice the way these points are written. For an x-intercept, you want the y-coordinate to be 0. For the y-intercept, you want the x-coordinate to be 0. So intercepts are actually points. These are places where the graph will intersect the axis. Sometimes they intersect and then go back up. Sometimes they intersect and say, well, we sometimes refer to as going through the point. So this one doesn't stay on the same side, it goes through. You'll see later that makes a difference when you're solving equations and inequalities. So you got that type of behavior for this graph and this graph and this graph. But these two graphs are slightly different because you have the intercept, but instead of the graph going through off the screen there, it kind of hits the intercept, goes back up, or just kind of turns around. So one of the things we'll be doing, I think it's section 1.5, talks about transforming graphs and coming up with new functions, starting with the graph like this, moving it left or right, moving it up or down, flipping the graphs, stretching graphs, and shrinking graphs. So if you know what the toolkit function looks like in the beginning, you could then apply a series of transformations to get a new graph. So a new version of a linear function, a new version of the square root function, a different looking absolute value instead of one that looks like this. Maybe it's a little bit narrower. Maybe it's been moved left or right. Maybe it's been moved up or down. Maybe it's been flipped. So kind of describing what's going on in relation to the basic toolkit function. So we'll be doing that in the, I think it's section 1.5, yeah. All right, give you a chance to do a screenshot here. It's pretty much like the classroom because the classroom has whiteboard and then the big screen where I show you the computer stuff. Can't keep a whole lot on the board there. So any questions before I start with the new screen here? Anything? All right. Okay. In section 1.2, another thing they talk about is this idea of a piecewise defined function. And I really like our textbook. I'm not a particular fan of this section because I think they do it a little too early, in my opinion. But if you can at least understand how a piecewise function is defined. A lot of functions are defined where the outputs are essentially one formula. You give me x, here's the way we calculate y. A piecewise function has more than one output in terms of a formula. So if I take a number that's bigger than or equal to 0, maybe I define the first formula to be like x plus 1. If I take a number that's less than 0, maybe my second formula is going to be something like 2 minus x. So if we think about the toolkit functions, x plus 1 looks a lot like x. 2 minus x looks a lot like x. But you can only use this output if you give me an input that's bigger than or equal to 0. So the first thing to help you understand how a piecewise function works is which formula do you use if x is 2? Which formula do you use if x is -1? Which formula do you use when x is 0? So it's kind of backwards. You kind of would expect the if-then statement to start here. It actually starts here because these are the inputs. So you have to say, is 2 bigger than or equal to 0? Yes. If it is, we use that first formula. So one point that's on the graph is 2, 3. -1, on the other hand, is not bigger than 0, so we will not be using the same formula. -1 is less than 0, so we will be using the second formula. Get the same output. So these are both points on the graph. And then for a piecewise defined function, if there's more than one part, you're probably going to have to split the definition up at a given value of x. 0 is the dividing line. But look at the way the function is defined. The first formula, x bigger than or equal to 0. Second formula, x is less than 0. So where does 0 fit into the inequalities? Top one. So we're going to use the first equation. So f of 0 is equal to 1. You might ask yourself, what happens if I define my piecewise defined definition this way? X is less than or equal to 0. X is greater than or equal to 0. What would happen if I give you 0 as the input? Which formula would you use? Well, according to this, you would use both formulas. And then we would have a problem because these 2 points both claim to be on the graph of your function. They both cannot be on the graph. When x is 0, we just want to get one output. This one produces 2 outputs. So we would not have this defined if we want to talk about a function. So don't even write that down. This is the point you get when x is 0. The other thing you have to watch out for here is, what does the graph look like? Usually you get a couple of points, you play connect the dots, everything looks good. Here, what happens when you try to play connect the dots? Those are your 3 points. How are you supposed to connect the dots? We know this is a straight line. This is a straight line. Look at those 3 points. How are those all going to go through the same straight line? They're not going to. And that's because these are 2 different lines kind of coming together. So in order to graph this, you need 2 points that are on this line. So if I were, say, for example, use 0, 1 and 2, 3. I know I can draw a line through those 2 points. For the other equation, though, I'm going to need a second point to figure out what that looks like. So let's use maybe -2. So 2 minus -2 would be equal to 4. So the point -2, 4 is also on the graph. So here is -2, 4. So the graph will pass through these 2 points right here. Just pretend that's a straight line. It's a pretty bad line. Okay, now don't be deceived here. It looks like they come together here at 0, 1. For this particular example, the 2 parts of the graph actually do come together. And you can see that if I used, for example, 0 here, no, scratch that. I should have drawn a better line here. I was about to say these 2 parts are supposed to come together. They're not supposed to come together, because if I were to draw this accurately, you can see that if I were to draw this part of the line, still not a very good line. I'm not getting closer to this point. I'm actually getting closer to this point right here, which is actually 0, 2. So when you draw a graph for this part of the graph on the other side, 0, stays on this straight line and gets closer and closer to this point, not to this point. So you actually have 2 lines that aren't really coming together. And that's what happens a lot with these piecewise defined functions. And that, to me, is why it's harder to kind of understand them in the beginning. in the when you're graphing them in particular, I think you can understand where the outputs come from and know which part of the formula to use. But coming up with the graphs, it's a little advanced, I think. Talk about them in the first chapter, especially if you don't have enough knowledge of these other types of functions that you might be using. I looked at some of the examples in the book. They're like cubics and square roots that we haven't even talked about yet. So that's why it can get a little complicated. So here's what the graph looks like. What's the domain and what's the range for this function? Are there any x values we cannot use? It looks like we can use them all. But for the range, you're looking at the graph, we definitely have some restrictions on range because the lowest number in the range is 1. Is any number bigger than 1 also going to be in range? Yes. Any number less than 1? No. So you can write this one of two ways. I'm a fan of the inequality notation because when you're using the inequality notation, you always are saying domain, x values, range, y values. You could also use interval notation. And it looks good, but it doesn't tell you whether this is a domain or a range. You're not using x and you're not using y. So either one of these two representations is fine. You can use either one when you're doing your homework for me. But when you're doing the online homework, you need to make sure to follow the directions. If they want it as an inequality, do it this way. If they want it as an interval, you have to write it down this way. Back in the old days, we used to do number lines as well, but I think most of our online homework systems don't even worry about that anymore. It's interval, interval, interval. The other thing that's kind of difficult to do here is how do you do a piecewise defined function on graphing calculator? You can type in the two separate equations, no problem. But if you do this on a calculator, you don't have to write this down. I'm just going to show you what you're going to get. You would get this. And you look at that and say, wait a minute, that's not a function. And you're right. How do you get the restrictions? Because you have to tell the calculator, oh, only graph this for x bigger than 0. Only graph this one for x less than 0. That's not an easy task. So I can just get rid of the red part of the graph there. There we go. Oops, went a little bit too far. It was just an excuse to draw a straighter line. Right, so there are a couple of homework problems like this. Don't worry too much about the graphs at the moment. Just make sure you understand the definition of why we call this a piecewise defined function. There's a value for x and we're using one output formula and then another set of x's we're using a different. Some of these might have 3 parts, you might have 4 parts, there might be lots of different parts. This is one of those questions we talk about in calculus. The calculus question related to this would be, what happens to this function as you get closer to 0 from the right? What happens to this function as x gets closer to 0 from the left? And that hopefully you can see on either side of 0, the function's not doing the same thing. It's not approaching what we call the same points. And that makes a difference when you're analyzing this function and talk about the idea of continuity, for example, or whether the function has an or instantaneous rate of change at this point. So in calculus, we need to know, will those two match or will they be approaching different numbers? So whether you can graph it or not, you can still analyze it the same way. Okay, any other questions about that for now? Give me a chance to do a screenshot here. And let me clear this off. And then this is something we had done an example for on Wednesday. So we're not going to spend a lot of time in this section, but just telling you the different ways in which you can calculate what essentially is a rate of change. And really what we're doing here is an average rate of change. If I give you a point on the graph of a function and a second point on the graph of a function, and I say calculate the average rate of change of this function starting at this point, ending at this point. You figure out how far you're going in this direction. How far are you going in this direction? The book uses the notation delta y and delta x. Delta means change in this representation. So that's the Greek letter delta. So how much does x change? How much does y change? So if you know what those two are going to be, you just take their quotient. That's how a slope is calculated if you have a straight line. But this is a more general question about starting at a particular point on a function, ending at a second point. So you could do this with a table of values. So if I give you this table of values of a function, you say, boy, those outputs are getting pretty big. But if I were to ask you for the average rate of change, I would never just stop there, because you can't just say, what's the average rate of change? Unless the graph is a line where it's always the same, you need a starting point, you need an ending point. So the starting point would be given to you, and the ending point would be given to you. So if I change my 1 and I change my 4, my answer is not necessarily going to be the same. So how do you calculate the average rate of change of this function from x equal 1 to x equal 4? You're going to need to know the corresponding outputs. So if we go back to the picture here, this could be the point 110. This could be the point 435. How do I calculate the change in x? 4 minus 1. How do I calculate the change in y? 35 minus 10. Which is exactly how you calculate a slope. So it's not necessarily a straight line through the 2 points, but that is what you're calculating. You're calculating the average rate of change, just like you would do a slope. So kind of picture this as a straight line through these 2 points. So this is your average rate of change. So y goes up by 25 as x goes up by 3. So whatever you want to write that answer as, I guess that would be, I like 25 thirds. As a decimal, it's going to be one of those repeating decimals, so 25 thirds. But if I change my inputs and outputs here, if I started at 0 and went up to 5, I'm going to get a different answer. The output at 5 is 47. The output at 0, 7. So one thing you could say in the end is over which interval is the function changing more on average? From 1 to 4, there's your answer. From 0 to 5, there's your answer. Which number is bigger, 40 over 5, 25 over 3? You would vote for 40 over 5. So we're not saying that as you go from 0 to 5, everything's going up by this number as you go up by 1. It's just saying on average. If x goes up by 1, y values go up by 8. So you kind of think of it as a nice little step until you get to this point right here. So the outputs would match up at 0 and 5. There might be more than one way to get there, but the answer on average is about 8 units every time x changes by 1. So you can use a table of values. You can get the answers from the graph of a function. you could also use the equation. So if you have a quadratic function, and I say find the average rate of change, from x equals 0 to x equal 2, you can then kind of generalize this statement that you see right here. F of 2 is the output here. F of 0 is your output here. And then you're going from 0 to 2. So these two numbers right here go in the denominator. So the only difference here is you don't know what the outputs are until you evaluate the function at those 2 points. So f of 2 is going to be 2 squared minus 1. F of 0 is going to be 0 minus 1. You just calculate that way. So there's your average rate of change. So you can be given a formula, you can be given a table of values. Now, something you have to be ready for here is what happens if you want to find the average rate of change over a different interval. And sometimes they give you the interval. F of 1 is your starting point. So think about this as your starting point. Look at your ending point for this one. 1 plus h. First thing you're probably thinking is, what's h? It's an unknown. So if you follow the same steps as you did here, this is the second output. It's kind of this number right up here. This is the first output when x is 1. That's this number right here. And then in the denominator, you're doing the difference of the x's. 1 plus h plus 1. So this answer will not be like this answer because it'll involve an h. So you actually have to do 1 plus h squared minus 1. F of 1 is equal to 0, so minus 0. All divided by h. 1 plus h minus 1 is equal to h. Now, you probably have done this calculation before. It's called the difference quotient. And kind of give me another calculus preview here. We ask in this question, what happens to this expression as h gets close to 0? So one reason for doing this is we can do a whole bunch of these average rates of change quickly, not over a set interval, but over an interval that involves this unknown. So if this number is very, very small, these numbers are very close together, how much are the outputs changing on that particular interval? So for us, all we need to do now is calculate it, and then we'll analyze it later. Now this can be simplified, but I just kind of left it in this form right here, just showing you that your answer will be in terms of h. All right, any other questions about that? Anything else? Give me a chance to do a screenshot here. The next two sections in chapter 1 talk about forming new functions from old functions. Now, one way to do that is to do operations. So these are in section 1.4. So I'll just say new functions from old. So you can add functions together, you can subtract, you can multiply, you can divide. So the usual operations. There's one way to form a new function from an old function that's not really corresponding to any of our usual operations. We'll show you how that works. So here is an f of x in a formula. Here is g of x in the formula. So if I say form a new function by adding these two formulas together, you would add a linear function to a quadratic function. I say divide. X plus 2 divided by 2x squared minus 1 would be a different function. Multiplying them would give you a third degree polynomial. So the first thing we're going to do here is see if you understand the function notation. This is read as f of g of 2. What does that mean? We're actually doing two different calculations here. If you know how order of operations works, 2 is our input. We're going to find g of 2. So we need to take one of these formulas and find the output. But because we're following order of operations, we do inside first, then outside. So the first thing we're going to do is find g of 2. So put 2 in for x here. There I get 7. Now, if that's all we had for this problem, we'd be done. But that's not all we have for this problem. This input of 2 produced an output of 7. But now that 7 is going to be used as the input for another function. And that function is f of x. So the second step here is to take f of 7 and do 7 plus 2. So f of g of 2, putting both of those together, is actually equal to 9. So it's a two-step process. What do you do first? What do you do second? If I switch the order of the functions, do you think the answer will be the same? Possibly, but if you've done enough of these problems, I think you'll know that in general, this is not going to be true. So f of 2 is equal to 4. What do I do with the 4? Replace f of 2 with 4, and now try to find g of 4. So I put 4 in for x here. So 16 times 2 is 32. 32 minus 1 is 31. So definitely not the same answer. So this is sometimes referred to as an operation. It's actually known as the composition of two functions. So if you're using two functions, it's a two-step process. And the key here is this number, 7, is kind of a dual purpose number. It is the output of g when I put 2 in for x. It's also the input for f, because that's the second step of the problem. So this number's got to be in the range of the first function, g of x, plus in the domain of this function. So 2, of course, has to be in the domain of the function you start with. And then 9, of course, has to be in the range of the second function. But this is the key right here. This number has to be both in the output of g, or sorry, both in the range of g and the domain of f. So you're kind of looking at two sets kind of intersecting. You need to make sure that number is in both of those sets. Now, in this example here, there are no restrictive domains, so you shouldn't have to worry about whether this number will be in both. But that might be an issue in some problems where the domain and or range might be restricted. So some books try to make this composition look like an operation by using what's called the circle notation. It's an open circle, it's not filled in. Filled in might make it look like a multiplication. I'm not a fan of this notation because this is how you would write it when you're doing this problem. And to me, this is a lot more specific. It tells you exactly what function you're applying first, what function you applied second. So even though these two are the same, you should be ready for this notation for problems you'll find in the book or you might find online. I will always write it this way, because then I know exactly what is my input, which function do I apply first, which function do I apply second. So this is sometimes read as the composition of f and g. But when you say it that way, you say f of g, you say g of f, order makes a difference. So this representation here and here, there's no question about the orders. You know exactly what to do first. You know exactly what to do second. So when you start saying, oh, it's the composition of the two functions, you can't just say it that way. You have to say composition of f and g, apply g first. Or the composition of f and g, apply f first. Because those are not going to give you the same answer. So one of the things you do in calculus, it's very important to identify when a function has been composed with two other functions. So kind of showing you what's happening here, f of g of x is a formula for this general calculation that you see right here. And here is another question, see whether you understand how function notation works. So f of g of x. G of x is 2x squared. That's 1. So what does this mean? How do you evaluate f at 2x squared minus 1? Remember, that's just a placeholder. Whatever goes in the parentheses, whether you call it x, whether you call it h, whether you call it a number. Replace x in this formula with this right here. So here's x, which is now 2x squared minus 1 plus 2. So this would be a general formula that'll work for any value of x. We did specifically for x equal 2. This works for any value of x. And then you can do it the other way, g of f of x. F of x is x plus 2. And hopefully by looking at these two formulas, you can see that they are definitely not the same formula. They're both quadratic functions, x squared, but not the same quadratic function. So if I give you something that looks like this is something you do in calculus. And I say, write this as the composition of two functions. Such that h of x is equal to f of g of x. This is where you take the answer and break it down into the two components that produce your function h of x. So a good way to think about it, just like you would over here, this is your input. What function do you apply first? Get an answer. Then what function do you apply second? Get an answer. So if you're looking at the formula here, are you going to apply this function first, this function first, this function first? If I give you x, what are you supposed to do first? You do x minus 3. What happens after you do x minus 3? To the third power. Then you multiply by 3, then you add 4. Those are kind of the steps that you would follow here. So x to x minus 3 to x minus 3 cubed to 3 times x minus 3 cubed. And then your final answer is right here. So these would be the kind of the steps you would follow in order to evaluate this function. So if you want to write this as a composition of two functions, I could use any of these representations right here and say, this is my first step, or this is my first step, or this is my first step. So one way I could write it would be, I'm going to say g of x is equal to x minus 3. So if this is my g of x, think of the other three steps as this x minus 3 replaced by g of x. So that means that f of x is going to be x cubed times 3 plus 4. So this would be one answer when you think about what the composition would look like. Now, that's not the only answer because this one is kind of a multi-step question. But if g of x was x minus 3 cubed, you take that as an answer, then all I have to do to get the answer is multiply by 3 and add 4. So another possibility would be, I want to make this a little too confusing here. would be x minus 3 cubed, and then 3x plus 4. So it's kind of like, where would you start when you're trying to form the composition? Would you start here? Would you start here? Would you start here? So you can see that either of these two representations would give you 2x. So this is another important calculus skill. And because, this is precalculus, not that you have to understand it right now, but there are a lot of things that we're doing, even in this first chapter, that are important when you get to calculus. Identifying a composition of two functions, calculating that rate of change, talking about these piecewise defined functions that don't come together. These are questions that are answered in calculus. Right, so any questions about that? It's in section 1.4, the idea of, they talk about all the operations, but I think the one you want to focus on is understanding what a composition is. So I think if you really understand how the function notation works, this will make a lot more sense. Replacing g of x with the formula for g of x. This was x in the formula for f of x. There it is in the output. So this is one way in which you can form a new function from the old function, is to do what's called a composition. The other one, or the other method you could use is in the next section, section 1.5. So I'll give you a chance to do a screenshot here. All right, now when we get to the section on college algebra, I try not to go too fast because there are some parts that are a little bit, take a little bit more time for students to understand. The idea of a transformation of a function. So this is taking, we'll start with our toolkit functions, taking it and doing a series of transformations. So you can describe them one of three ways. You can shift the graph left or right, up or down. You can take the graph and flip it. You can do either the x-axis or the y-axis. The third type of transformation is stretching and shrinking. So picture a linear function, for example, or a quadratic function. And doing a series of transformations on this that would produce a different quadratic function. Maybe one that looks like this. Start with a cubic function. Do a series of transformations on the cubic function that looks something like this. And how could you go from this graph to this graph? How could you go from one equation to the other? How could you describe it in words? So the three different types of transformations are shifts. And these could be vertical or horizontal. You can do flips, reflections, over the x-axis or the y-axis. Or you could do stretching or shrinking. And once again, that can be described vertically or horizontally. So when I'm sitting here doing all these weird hand motions, you can kind of understand what's going on with the function. Trying to do it on a particular graph, trying to do it with a particular equation, kind of hard to relate to sometimes. So these are the easier ones to do, because what happens is when you do a shift or you do a flip, what you do is you change the position of your graph, but you don't make it narrower or wider. So what we say is the graph is a rigid transformation. And rigid just means your parabola will be the exact same size, the exact same shape, just in a different position. So if I take my parabola, I move it left or right. I didn't change the size or the shape, I just changed the position. I flip the parabola. So flip it over the x-axis, for example. Once again, same size, same shape, just a different position. If I take the graph and move it up or down, same thing is happening there. So these are called rigid transformations. When you look at stretching and shrinking, however, this is going to do one more change to the graph. So if I take my parabola and I make it narrower, or I make it wider, it's still a parabola, but the size of the graph has changed. So it's still a parabola, still same shape, but the size has changed, whether it's narrower or wider. So I kind of put these in two categories. So rigid versus non-rigid. I think it's easier to understand how these vertical and horizontal shifts are going to work if you're just looking at a picture. So if you start with a parabola, and I say move this graph 3 units to the left, you would draw a graph that was 3 units to the left. And what you do is you take a look at all the points being shifted 3 units to the left. That point right there is 0, 0. This point would be negative 3, 0. All the other points would move accordingly. If you think about the equation, though, of the original graph, so Toolkit function x squared, what's the equation going to be for the shifted function? One way to think about it is if you're shifting something horizontally, what changes, what stays the same? What's going to change here are the inputs. The outputs actually don't change at all. Your range doesn't change. You still have 0 as the input, 0 as the output here. But notice that 0 is the output for -3 in the shifted graph. It is the output for 0 in the original graph. So if you're doing something to x before you square the function, that's a horizontal shift. What can I replace x with here if we're going to be shifting it 3 units to the left? This is where it might get a little confusing, but if you think about where this point ends up, -3 means you went 3 units to the left. Does it make sense to write x minus 3 here? No, because if I put 0 in for x here, I'm going to take away 3 first and then square it. That's not the same answer as I get here. So it should be x plus 3. X plus 3. So I shift up 3 units to the left, x gets replaced by x plus 3. If I shift it 2 units to the right, this point becomes 2, 0. And think about what that equation would look like. It's not x plus 2, it is x minus 2. So horizontal shifts, the equations might work a little backwards to what you might expect. This is x minus 2, that's going to the right. X plus 3 goes to the left. Fortunately, vertical shifts work the way you would expect them to work. So I say, what is the graph of x squared plus 4 going to look like? It's the graph of x squared moved up 4 units. What's the graph of x squared minus 9 going to look like? That's the same graph of x squared moved down 9 units. So the two shifts, verticals, work exactly as you expect them to, equation-wise, picture-wise. For the equations for the horizontal, gotta be a little careful. X plus 3 goes to the left, x minus 2 goes to the right. And then when you flip your graph, there are 2 different flips you can do here. Actually, this is not a good graph to do this for. Let's start with another one. Let's take the graph of, use the Toolkit function x cubed. Now we're asking you to draw a graph of a function that was flipped over the x-axis. So when you do a flip over the x-axis, everything that was above the x-axis is now below the x-axis. Everything that was below the x-axis will now be above the x-axis. So here's the flip. And then the question is, what would the new equation look like? So think the same as you did here and here. Plus 4 means after you graph x squared, it moves up or down. So you do something to the outputs. Here, what's changing are the outputs. So x stays the same, but the outputs become the opposite. So to flip it over the x-axis, it becomes negative x cubed. If you flip the graph over the y-axis, instead of doing the negative out front, you do the negative x first. So this is a flip over the x-axis. This is a flip over the y-axis. But once again, you can see it's a rigid transformation. It's still the graph of x cubed. We didn't stretch it. We didn't shrink it. We just changed its position. So this is your flip over the x-axis. And this is your flip over the y-axis. So what you want to be sure to do here is relate the picture to the equation. So what you do here can be described in words, you can then draw. What you do here can be described in the equation. And then you could write down the description here. So I think, to me, it helps going back and forth between the different representations. Describe it in words. Tell me what the picture looks like. Give me an equation. You should be able to go back and forth between all those representations. One that may or may not be helpful would be looking at a table of values. So if you have a table of values, and I say, tell me what the transformation would look like here if I shifted everything 3 units to the right, for example. If you look at what happened with the parabola, remember all the outputs stayed the same and the inputs were adjusted. So if I want the new function here that's going to be shifted 3 units to the right, I'm going to start with the exact same y values. What's going to change, though, is the x value that corresponds to that y value. So if I go to the right 3, this point moves to the right 3. This point moves to the right 3. This point moves to the right 3. And then again, new set of values here. So the values, notice that y stays the same, x changes. How did x change? Everything went up by 3. So your new equation would involve an x minus 3. So you don't need a formula necessarily. If you had a picture, I think you can see how the picture, all the y and x values have been adjusted. Now that's one thing students are kind of, it's almost like their mindset is, you always need a formula for a function. I need to know what the picture looks like. That's not necessarily true as long as you have something that can be described using the definition, for example. So if you have a situation in which it is a function, whether you do it in words, picture, table, et cetera, you should be able to work with that particular representation. So you don't necessarily have to have it as a table or necessarily have to have it as a graph. Because it's true, I don't know what the formula is here. 5, 7, 8, 9, 12, I just made them up. And I just made them up. It still satisfies the definition of a function. So the ones in which we can go back and forth between the different representations are probably more useful to us, but you still want to be ready for these other ones. Right. Any other questions about that? Let me show you one more thing. We're just about out of time here. Actually, do a screenshot here. I'm going to erase a couple things. I just kind of want to show you a picture of what's going on with these stretches and shrinks, and we'll kind of finish this up on Monday. Because I think the pictures help you understand the stretching and the shrinking. It's relating the pictures to the equations. That's going to be a little bit more involved. So if I start with a parabola, if I did a horizontal shrink on this one, I would take the parabola and make it wider horizontal. So my parabola would now look like this. So something like that. So a wider looking parabola. So this is called a horizontal shrink. Sorry, this is a vertical shrink. I'll get it right. Because if you think about the graph, it's wider vertically. If you start with the parabola, and draw like this. This is a vertical stretch. So it's narrower than the original parabola. It's almost like you took the parabola and yanked it in this direction. Whereas in the other one, you took the parabola and kind of pulled down on it. Pulled down. The issue here is a vertical shrink is also the same as a horizontal stretch. Those two actually are describing the same thing. A vertical stretch is the same as a horizontal shrink. And a horizontal shrink just means that if you start with this, this is narrower. If you think about it horizontally, you take the graph and pinch it like this, it's narrower horizontal. The other graph, if you take it and pull it out this way, it's a horizontal stretch. So the equations are going to reflect that, but that's why I think this is a little bit more confusing concept, is because this could be thought of one of two ways. This could be thought of one of two ways. And then with the equations and the horizontal, it's kind of like this here. It's the equations are going to end up being opposites of what you might think. But the key here with stretching and shrinking is when you're doing shifts, notice it's +3, -2. X squared plus 4, x squared minus 9. Everything is added and subtracted. With stretching and shrinking, it's going to be multiplied. And that's where you start changing the shape of the graph. So if all the outputs get multiplied by a factor of 2 instead of being added, that's where the graph gets stretched out or shrunk. So we'll take a look at a couple of those equations on Monday, finish up the rest of chapter 1. Chapter 2, I don't think will take us very long to do. But let me give you a chance to do one more screenshot here if you want to. I just want to go back to the calendar here for a minute. If you look at the first online homework, which is due Monday, it's only over the first 4 sections. So we definitely went through all that today, and that's what the weekly homework number 1 is for. And then the rest of chapter 1 will be due at the end of the week. So if you want to keep working on all of those, go right ahead. But the first 2 assignments right here have to do with sections 1.1 through 1.4. So those are the ones, of course, you want to do first. All right. So any other questions for now? Anything else? Well, I will be seeing everybody on Monday. Let me know if you have any questions as you're working on things over the weekend. And have a good weekend, everybody.
Thank you.
Thanks.
Thank you.
Have a good weekend.
You too.
Thank you.